So, hello everyone. So, in this lecture of vector algebra, which is basically lecture 6, we will discuss the orthogonality of two vectors and we will see some nice properties of such vectors. Okay. So, let us define what is orthogonality of two vectors. Okay. So, let A and B are two vectors in Rn, then we say that A and B are orthogonal to each other if A dot B is 0. Okay. So, orthogonality also has a name, it's perpendicular. So, orthogonality is also named as perpendicular. Okay. So, this is a note. Okay. So, basically we say that A and B are perpendicular if their dot product is 0. Okay. So, we will see what are the consequences of this fact, okay, of two perpendicular to orthogonal vectors. So, one observation, let A dot B is 0, where A, B are in Rn, okay. Then, what is this quantity? Norm of A plus B whole square. As you have seen earlier, this is exactly this plus this plus this. But if A dot B is 0, that means the middle term will vanish and we will exactly get this. So, this is somehow a very nice identity, and this square actually distributes with only the vectors. There is no intermediate terms, and this is called Pythagorean identity. Okay. So, this is orthogonality. Now, we will find the angle between two vectors. Angle between two vectors. Okay. So, how do you define that? So, let A and B are two vectors in Rn such that B is not the 0 vector. Okay. Then the vector T multiplied with V, where T is the scalar given by A dot B by B dot B. Note that B dot B is strictly positive because B is not the 0 vector. This vector TB is called the projection of A, of the vector A, along the vector B. Okay. If both A and B are non-zero, the angle theta between the vectors capital A and capital B is defined as theta equal to cosine inverse A dot B by this. Okay. Now note that this quantity A dot B divided by norm of A into norm of B is always less than equal to 1 by the Cauchy-Schwarz inequality, and this is always bigger than equal to 1. So once we have this, we can say that this says that 0 less than equal to theta less than equal to pi. Okay, and if a dot b is 0, then this angle theta is pi by 2. Only thing is that we are assuming that both vectors a and b are non-zero. When we have defined the orthogonality or perpendicularity, a and b was arbitrary vectors. They may be 0 or non-zero. Okay. So basically, when you are finding angles, the two vectors should be non-zero. Okay. So we'll only define one thing, that is basically one property of this orthogonal vectors that we have defined, and it says that if you have, let's say, two orthogonal vectors, they will be linearly independent. Okay, so how do we say that basically? So instead of two vectors, we can define a set of orthogonal vectors where we say that if, a definition is orthogonal set. So a set S equals to A1 to AK of vectors in Rn is called orthogonal if ai dot aj is 0 whenever I is not equals to j. In other words, any two distinct vectors in an orthogonal set are perpendicular. Okay. So this is one theorem that we are saying, is that any orthogonal set S equals to A1 to AK of non-zero vectors in Rn is linearly independent. Okay. Moreover, if S spawns a vector capital X in Rn, say if x equal to sum over I equal to 1 to k ci ai, then you can actually find what is this component ci. This is x dot aj divided by a j dot aj, j equal to 1 dot k. So the proof is, we will divide the proof into two steps. First we will prove that S is linearly independent. So to this end, suppose that I equals to 1 to k ci ai is 0. Okay. So what you will do, you multiply with aj. When, so if you split this is basically c1 a1 plus c2 a2, it will go up to ck ak. Okay, and this is the zero vector. Okay, the right side is the zero vector. Now let's say you want to prove that c1 is 0. Okay, so multiplying, basically taking the dot product, that means taking dot product with a1, we get c1 into a1 dot a1 is 0 dot a1, which is 0, and that means that c1 is 0 because a1 dot a1 is not equals to 0. Okay. Similarly, you do the same thing. If you want to prove c2 is 0, you take the dot product with a2, you get that c2 is 0. So C2 is 0, and similarly you can say that Cn is 0. So all the Cn's are 0. Okay. So if one of the vectors is 0, let's say this, let's say if a1 is 0, then you cannot do this, because c1 and a1 dot a1 is again 0. So you cannot say that c1 is 0. So you can take c1 to be non-zero then. In that case it will be linearly dependent. But here you can see that all the constants will be 0. So linearly independent. Now what is remaining? Okay. So what it says, the second property. So if this set of orthogonal vectors spans some vector x, capital X, so basically then you can find what is the component, what is the coefficients. Okay. So if x is equal to this, so what we will do, again you use the orthogonality. Okay. So let x equal to sum over I equal to 1 to k ci ai. So if you split this, you will get that this is ck ak. So now you multiply with, let's say, x dot a1. Okay. So you'll get c1 into a1 dot a1. The remaining terms will be 0, right? Because ai dot aj is 0 whenever I is not equal to j. So it's better if one writes the same thing here also, and this is 0 when we have I not equal to j for every. Okay. So this says that c1 is x dot a1 divided by a1 dot a1. So similarly you will find that cj is x dot aj divided by aj dot aj. Okay. This is what I wanted to prove. So it somehow gives a characterization of the orthogonal set. Okay. So this is linearly independent. Also it takes some linear combination. If it is some vector x, then the coefficients of the linear combination can be found using the orthogonal vectors in that set. Okay, where we use the knowledge of dot product. In the next lecture, we will discuss some applications of vector algebra to analytic geometry. So we will stop here.